In this video, we're going to look at question 5 from page 43 of the course notes. So in this question, we've been asked to find the maximum bending stress in the beam. So immediately that tells us that the formula we're going to be using is one for maximum bending stress. This is our formula here as a reminder. Maximum bending stress is equal to bending moment times the distance from the neutral axis, so the centroid in the cases we're looking at, and the centroid to the furthermost part away from the centroid of the beam, divided by the second moment of area. And in this question, we're not given any of these three pieces of information straight away, but we can determine each one of them: the bending moment, the second moment of area, and that distance y from the centroid to the extreme part of the beam. So let's start with y. It's actually a relatively easy thing to find. So y is going to be the distance from our centroid, is going to be the line indicated across here. And y is the distance from this line, not to the midpoint, we'll deal with that in a second, but to the very end of the beam. So this is half of the depth of our beam. So half of 325, that's the total height. So our value y is 325 divided by 2. And that's going to be 162.5 millimeters, because that's the units we're working in. It doesn't actually say on the diagram here, but we assume with numbers like this it is millimeters, and we will state clearly in any assessment question. So that's great. We've ticked off y, we know that. M we need to find. Now we found maximum bending stress several times in the early part of the course, but here what we can do is use one of our standard cases from page 19 of the course notes. So where we have a simply supported beam with a UDL applied along the length of it, we can use this formula here, and you'll find this in page 19, example 3. Maximum bending moment is given by this WL squared over 8, where W is our UDL value, that's 12 kilonewtons per meter, and L is our length of our beam, that's 9 squared, and dividing by 8 completes the formula. So we put those numbers into our calculator. We get 121.5. That's in kilonewton meters, because force and then length are our units for bending moment, and we are working in kilonewtons and meters in this question here. And right now, we'll take a moment to convert this into Newton millimeters, because that's what we'll need in our question later. So this, if we multiply by 1,000 over 1 to get from newtons, kilonewtons to newtons, and multiply by 1,000 to go from millimeters to meters. Now, I know this is right, is that we've got meters here and meters in the top, and meters in the bottom here, they cancel. Kilonewtons here and kilonewtons in the bottom, so they cancel out. So we're left with newtons and millimeters, which is what we're looking for. So times 1,000 times 1,000, what we can say is we're going to have 121,500,000 Newton millimeters. But we'll tidy that up a little bit, because that's quite a lot of decimals. So 1.215 times 10 to the 8 Newton millimeters. Now rub this out just now. These this working for the units, just so we've got a bit less space. So this is our value here for M. But the last thing we need to find, so we can use our formula, is I. And it's Ixx in this case, because it is the second moment of area about the x-axis. So how do we find this? Well, if you remember from earlier in the course, the parallel axis principle, where we can divide up our I-beam into 3 separate rectangles, 1, 2, and 3, and the top flange 1 and 3 are going to have the same second moment of area, and the middle section we'll have to calculate separately. So how do we do this? Well, we first of all note that the centroid for the flange is not the same as the shape. We need to take that into account. So the centroid of the flange runs through the middle of its depth there. And so we've got this distance C to consider, which we'll need for our calculation coming up. and C is the distance from the centroid of the flange to the centroid of the whole beam. So it's half of 325, but then minus 10 because it's coming halfway down the flange. So our value for C, we'll need this here, C is 162.5, which is actually our value for Y, minus 10 to give us 152.5. So this value here, this is C is equal to 152.5, because this is something we have to factor in for any part of the beam which doesn't lie along the centroid of the whole beam. So let's work out for each rectangle. So for rectangle 1, and this is also going to be the same for rectangle 3. For rectangle 1 here, we've got IXX is equal to BD cubed over 12, which is what we'd expect for a rectangle. But we add on this bit here, AC squared. A is the area of the flange, and C squared is this value, 152.5. So let's put in our numbers to see what we get for this. The breadth is 150, the height is 20. Our area is 150 times 20, because that's the breadth and depth of the rectangular flange, and we multiply by C squared. So this gives us a value, I'll just determine just now. This in 6986850. I'll write this a bit tidier in scientific notation. 69.869 times 10 to the 6. Again, our units are millimeters to the power 4 for this. So that's for rectangles 1 and 3. So 1 and 3 both have the same second moment of area. And for rectangle 2, that's the central part of the beam. Well, this does have the same centroid. If we think about our rectangle by itself, at the top here, line running through the middle of that is the same as the line running through the middle of the I-beam. So we don't need to consider AC squared for this part of the beam. So we can just do exactly what we do for any rectangle, do BD cubed over 12, which is equal to, in this case, well, the width of our beam is given in the question as being 10 millimeters, and the depth will be our 325 minus the 220s for the flanges. So this bit, I'll put it in green in the diagram, it's getting a bit crowded here, but this bit between the two flanges here is 325 minus 20 minus 20. So that's 285, that height there. So that would be times 285 cubed divided by 12. I'll put this into our calculator, and it's a bit tight in space, but we'll fit it in. And this gives us this number here, 192909375. And steal a little bit more space by shifting my screen up. And we'll put this in scientific notation as well, so we can easily add these up. And this is going to be 19.291 times 10 to the 6 millimeters per 4. So going back to look at our I-beams, I'll rub out all these markings so that we can have a better look at our I-beam again. So our I-beam consists of rectangle 1, top flange, rectangle 2, middle beam, rectangle 3, bottom flange. So we add all three of these values together to get the total second moment of area about the x-axis for the beam. So I'll do it down the bottom left of our screen. They've got 69.869 times 10 to the 6 for rectangle 1. We've got 19.291 times 10 to the 6 for rectangle 2. And we've got the same as the first one, 69.869 times 10 to the 6 for rectangle 3. The three of them, if we add them together, which I'll do now, get 159.029 times 10 to the 6 millimeters to the power 4. So I'm about to rub off everything from calculating the second motive area. So either pause or go back if you want to see that again. Rub this out here. And I'll underline the final answer for our second motive area just so we can see it's clear what we're using. So that's our value for IXX here. And of course, we had our value for Y up the top. So the three I've underlined in red, they're the three values that are going to go into this equation for maximum stress. So now we can put them all together. So we have our value for M, which is 121.5. Sorry, that's not what we got for that. We got our final answer was 1.215 times 10 to the 8. Our value for Y, which is 162.5, and divide that by our value for I, which is 159.029 times 10 to the 6. And if you're thinking, why is this not 1.59 0 to 10 to the 8? It's the same thing. I just chose to do that to keep everything nice and consistent to save me messing about with the decimal places, but that would be the same thing. So where you put the decimal place, the times 10, is a matter of sometimes neatness, but it's often helpful when we're working with things to keep them all times 10 to the 6, all times 10 to the 8, because it lets us add things quicker if we're doing things by hand and saving some time in the calculator, but that would have been the same. So let's put this in and see what we get for our maximum stress. I'm just putting that into the calculator just now. And this gives us an answer of 124. Now, our units here, remember, we converted M into Newton millimeters, and all of our lengths were millimeters as well, and our second way was millimeters to the power 4. So this means our units here are newtons per millimeter squared. And that is our final answer of how we get the maximum stress in a question like number 5.